Okay, so hello everyone. Good morning, I guess. So I will share my screen. So we'll be continuing today with the how to apply what we saw last time to bootstrapping effective field theories. Can you hear me well?
Yes, I can hear you. We can hear you. Yeah.
Great, thank you. So let me spend a few minutes to recall where we were, and then I will state exactly what's the plan for today. So last time we discussed causality, why we care about it, and what it tells us about waves. So when you have a wave, it's Fourier transform. We learned that well, the transverse function, which tells you our wave is transfer, is analytic in upper half plane. And there's some condition of non-exponential growth, but if you have unitarity, the growth condition gets much stronger. And in addition, you get that it's bounded in the full upper half plane. So our idea is to apply those two conditions to scattering processes. So we study things like 2-to-2 scattering amplitude. Some process like this, time goes up. We have some wave here, it comes out in some wave, and we hope to say something along the line that if the wave here is vanishes before some time, then so does the output. Okay, and it's related to the idea that measurements at infinity should commute when they're space-like, at least when we have some well-defined notion of causality as we have at infinity. And we've argued that this leads to some analytic property of the S matrix. There's some branch cut stuff, weird place in the middle that we want to avoid, and some boundedness property that we'll discuss. One thing I should stress here is that I think what I presented is a compelling picture of the why crossing symmetry and analyticity are true for scattering amplitude and why you should believe in them. The actual proof of these statements are surprisingly non-trivial. Even in axiomatic field theory, where we understand the rules of the game, it's surprisingly hard to prove these statements. As we discussed, it has to do with the fact that, well, the things that commute space-like, they're not the things that we usually use in the LSZ reduction formula, which has finite angle scattering. So connecting those two limits is non-trivial. But I think it's, instead of the technical proof, I think it's important to have a good picture in mind for why we should believe in these things. So that's what I try to convey. And the other property that's going to be important is that if we scatter things that are normalizable as a function of a transverse plane, so we introduce this concept of smear amplitude that is going to define it slightly differently from last time. I'm not going to put a 1/s factor in front. If you smear scattering amplitude with momentum transfer minus p square with compact support in momentum space, then the idea is that this thing here will be at large S. Maybe let me make some more room. It behaves like a function of energy less than some constant times the power of S. Generally, we set the some exponent. You could try to parameterize it. You could try to bound it to some power. And what we showed last time is that this power is less than 1. I'm going to call this power J0 for today. And the principal property of this smearing is that it's compact in momentum space. That's needed so that the integral has nice analytic properties and involves physical quantities when the moment, we're at enough energies. And it also is normalizable in impact parameter space. We need to scatter normalizable things that have finite momentum support. And for these things, I think this property is very straightforward, transparent interpretation, and that's what we're going to use today. So this lecture will be about the EFT Bootstrap, or at least trying to constrain effective field theories. We're not going to necessarily narrow down interesting effective field theories, but we're going to constrain the space and learn about the general structure of any effective field theory, even if the UV completion is very strongly coupled and we can't access it otherwise. So this lecture is again going to be split into a few short parts. So I'm going to explain first how these NLC properties and these things I've just mentioned gives rise to some rules that connect low and high energies, and then I'm going to go in depth into these factors. For the lectures, for all of these topics, I will introduce the ideas for scalar fields and then discuss how it generalize when you have spins and more rich setups. And there's some reference for this lecture. The scalar stuff will be based on this paper with Van Duong from a year and a half ago, a related paper about scattering of particles with spin, or EFT hadron, others, and the toolkit for an analytic matrix for this person. And a lot of the motivation for looking at these some rules which connect high energies and low energy come from earlier work, including this famous paper, which should be like mandatory reading. These articles about causality constraints on effective field theories. Okay, and tomorrow we're going to continue to elaborate more on how actually we deal with problems with inequality. So this is much more general than the S-matrix bootstrap. This is for any kind of bootstrap problem, and perhaps even in other areas of physics, it could be useful. Then I will describe specifically what happens when you add gravity to these effective field theories, some open questions. That's the plan. So how do we use these properties? So these NLC properties, well, the basic idea is to write down some integral that gives 0 because of the boundedness. So integral with some contour at infinity, 1 t, write down something like this, k plus 1, that's 1 plus k. Do some integral like this. That's a fixed t integral. In fact, it's going to be useful to, okay, so that idea is that this should give 0 if k is large enough. It's actually useful to offset it a little bit, the denominator. I'm going to put a minus p square over 2 here. And sorry, that's minus t. And I'm going to put t equal to the minus momentum transfer. And so yeah, so we have this thing. That's the denominator. This offset is useful because it manifests crossing between S and U channels. So it's basically S prime minus U prime over 2. That's nice for crossing. And since everything we do is going to have both a S channel and a U channel contribution, it's nice to have something that is crossing. Here I'm writing things for massless case, but you can do it for massive as well. So the contour we're talking about is this one. Basically, it's got the real axis, this plane, and we're doing a contour like this. I write it as a single contour around infinity, but you should keep in mind that it's really two disjoint arcs, one above the real axis and one below. We don't actually go through the cut. It's really the union of two half circles. And this is meant to give 0 after it's smeared, after integrating against these wave packets that have compact support and normalizable. Okay, I'm going to ignore these wave packets for most of this discussion and focus on this thing that I would call bk of p square. That's a cave sum rule. they sort of some rules. We call them dispersive sum rules because they're basically the same as k-subtracted dispersion relation. Okay, so it's similar to a k-subtracted dispersion relation that reconstruct that reconstruct the amplitude at for m or its derivative around s equal p squared over 2. Okay, so it's similar to a dispersion relation. Similar to dispersion relation, the idea is it converges if you put enough subtractions. And because of what we discuss, we know exactly how many subtractions we need. We know it would converge here if k is greater than this rate of growth. And remember that j is at most 1. So k greater than 1 are guaranteed to converge in any causal unitary theory. So this J0 here, I define here as the rate of growth at infinity. If the amplitude is symmetric under SU crossing, then all of the odd k sum rules vanish. So these vanish. For k equal odd, if amplitude is signature even. Signature, I'm introducing this word here. I'm not going to use it in this lecture, but so everyone has heard it, at least in their life. It's an old word from rigid theory, which just tells you which sign the amplitude change when you do crossing symmetry. So crossing symmetric amplitude is signature even. That's just what it means. And crossing is related to CPT, so it's related to how things change under CPT. But that's a different story. But yeah. So that's why this emphasizing the symmetry is useful, because if you emphasize the symmetry, you'd think you have some rule for each power of k, and you would indeed get something for each power of k, but you just get redundant information from the odd power, so they're not useful. If you have symmetry, then you should use it, and that's how we use it. We put that here. A second note I should put is that in a lot of the papers that, well, for example, I've been writing, but also others have been writing, we also use instead of writing this thing here, another way of maintaining the symmetry between S and U channel is to write 1 over SU to the k plus 1 over 2 if k is odd, or S minus U over SU to the k plus 2 over 2. So you can put the poles, instead of putting the poles at this weird place, you can put the poles at S equals 0 and U equals 0. Okay, equal even. And in terms of the conclusions and all the discussion that will go after, it's basically equivalent. So it doesn't, yeah, it's the thing that's important is the behavior at large energies. Just to the conventions. The thing we'll be interested to do is to look at effective field theories, and our goal is not to actually, if we were to use it as a dispersion relation, we would compute the amplitude at that value. This is not actually our goal. We're going to treat this as like low energy, so we don't actually want that amplitude. What we want is to relate high and low. So what we do is that we deform this contour so that it ends up looking like this, an arc, and we avoid this region of small m. So here we start with a contour that's at infinity. We put it in. So the contour we actually use looks like this. We have something like this, and give out the branch cut. And here, I want to connect scales above some arbitrary value m square to scale at that mass. And I can use a contour that looks like this. And the idea is that, well, if this contour is C, then integral C equals 0 tells us that something I would call, so this sum rule, bk of p square, we write as the integral of something equals 0. And we get two contributions. We get one contribution from scale of order m square and one contribution from above. They have to add up to 0. So we get the all-important identity that minus bk p square, the low energy contribution, equal to plus bk square, high energy contribution. Okay. So this is a discontinuity because I'm going above minus below the axis. At energies greater than m. And this thing here is something that's computable with energies of order m. We call that low. And notice that I've chosen scale m that denotes my low and high energies. It's completely arbitrary in the sum rule. In a moment, this will be the cutoff of the EFT. But this is I've chosen it to be also tied to the limit on the transverse momentum. So the idea is that on this cut here, I want physical processes where the energy is above this m and the transverse momentum is below this m. So I'm guaranteed to have physical processes on this axis. And here, it's like some complex process that's not necessarily a physical process, but we can assume it to be a computable process in fluid theory, for example. So we can relate, the idea is to have some relation, or dispersion relation, or dispersive sum rule. Relate low and high energies. So this is the same physical insight as the Kramers-Kronig relation, for example, general or any other dispersion relations. If you have something that happens at high energy, for example, some resonance or something, you can produce particles. If something happens at high energies, it has to imprint at other energies. That's required by causality. That's what these sort of relations tell us. That's why they exist. Before we take a pause, let me make a brief comment about the spinning case. Okay. So in general, when you have spin, the amplitude itself, you could write as a sum of tensor structures with polarizations. Let me just call it polarization structures. And polarization can be dotted into each other or into momenta. Times things that only depends on madness time environment. Okay? And various sub-amplitude. You could have various of these structures. When you scatter particle with spin, you have these two ingredients, and it's often convenient to separate them. And let me give an example where the sum is actually quite trivial. When you have massless particle in 4 dimension, for example, massless graviton in 4 space-time dimension, you could have a process that maybe have one. So graviton can have helicity +2 or -2. These are the two physical states of the graviton. And then you get an amplitude that is, it has some factors of you can think in polarizations, but in 4 dimensions for massless particles, we can also think in terms of spinor listed variables. And this amplitude here will look like some factor 1/4 to the 4, 2, 3 to the 4, simply because each spinor carries spin half, so you need 4 powers of them to get spin 2. So you get some factor like this. And then you have some function of Mandelstam that multiplies that. And you cannot avoid having these factors because if you didn't have them, the amplitude wouldn't transform correctly when you do a boost or a Lorentz transformation. So these factors are really required physically. And they pick up some important phases that the amplitude has. But when you pull them out, you get an amplitude that is going to behave differently at high energies, because our axiom says that the amplitude itself has nice boundedness property. That means that F behaves somewhat separate differently. And this factor here in absolute value, it basically goes like T squared, sorry, T4. Okay. So what this means is that we have 2 kind of dispersive sum rules here. We can have, well, this process here, I've chose that it's symmetric in the 2-3 channel. So we have fix T minus P1, sorry, P2 plus P3 square. At fixed T, well, multiplying by T4 doesn't change anything, and you still have a integral ds prime over s prime to the 1 plus k and s prime t converge. But when you look at fixed U dispersion relation, for example, U dispersion relation, now when you take I energy, you're also taking IT, because s plus t plus u equal constant, equals 0. This grows a lot, which means that this decays, right? This F vanishes, well, like 4 more powers. That means that the fixed U dispersion relation, now you can write something like S to the s prime over s prime to the k minus 3. And now it would be this function f. So I should have written it f in both cases. S prime, and if fixed U, then t would be equal to, maybe I should put t equal minus p squared in both cases. T equal p squared minus s. Both of these converge for the same criterion when k is more than 1. Okay? K greater than J0, or yeah, sorry, strictly equal. Yeah. Okay. So in our work, and I think it's a good convention, we label some rules not by number of subtractions, but by how good they converge. Okay. We say that a sum rule has spin k. We say that bk is a spin k sum rule if the idea of this notation is that if it converges on exchanges of a particle with spin j or less. And
spin j
yes.
sum rule?
Spin k. Yeah, spin, sorry, spin, particle spin j less than k, sorry. Thank you. For any particle of spin j. And yeah, spin less than k. And the idea is that like when you exchange a particle of spin j, you get an amplitude that go like s to the j. So if you have an amplitude that converge for exchange particle of spin j, we say that But if it converges for all spins less than k, we say that it's a spin k sum rule. Okay. So this with this criterion, the convergence criterion is always k greater than k0. Okay, so that's always our convergent criterion. And you can notice something quite amazing about, for example, this fixed U dispersion relation for gravitons is that, well, if I put k equal 2, or even, yeah, if I put, so the lowest case that k has to be an integer, the lowest case that converge abstractly is be k greater than 1, so it'd be k equal 2. If I put k equal 2 here, I don't actually have a denominator. I just have a numerator. So this phenomenon is called superconvergence. Sometimes the sum rule doesn't have any denominator. We'll see how useful this is below when we constrain effective theories. It's very powerful. And in general, it happens when the sum of the spins that you're scattering -1 is greater than this intercept. It's an interesting criterion. We can discuss more why it comes. But yeah, so here for graviton, 2 + 2 -1 is 3, and that's more than the maximal possible intercept, which is 1. So let me take a little pause here if you have questions.
Simon, can I ask a question?
Yeah.
Can you hear me? Yeah. So when you are writing down subtracted these, when you're dividing by the denominators, are you implicitly fixing some constants? I mean, for example, I could have divided by s prime minus s naught to improve the convergence. Yeah.
Yes. Yeah, the S naught doesn't change anything. So yeah, I'm focusing on the large S behavior. So in reality, yeah, in reality, in practice, oops, sorry, when we do calculations, sorry, it's completely, sorry, this completely disappeared. When we do calculation, we always choose these crossing symmetric choices, which are either we either choose this like this factor with an offset, or more often in our work we use this SU symmetric powers.
Okay.
But yeah, but the convergence is determined by the largest behavior.
Right. Sure. Sure.
Yeah.
Are there any other questions? Okay, I don't see anything. Yeah.
Okay, so we're going to use this to constrain effective field theories. So let me pose the problem. Okay, so the main concept here to remember is that we label the sum rules by roughly the number of subtractions, but more precisely, it's this spin of the Ricci spin of the sum rule. That's a uniform concept that you can apply to spinning or spinless dispersion relations. We're going to be considering effective field theories. So now let me discuss a bit about the low energy side of that, of those sum rules. So basic idea of an EFT is you think about different energy scales or mass scales, and there's some cutoff, and we mostly do experiments below the cutoff with scattering some stuff much below the cutoff. And an effective field theory is yeah, so let's discuss it in detail for the case of a single real scalar. Okay. The EFT is useful when parametrically the mass that of the things we're scattering is much less than the cutoff. Otherwise, there's not much reason to do a separation of scale. I want to do some kind of the idea of an effective theory is to do some expansion in 1/n. Okay, so we're just going to assume that we're massless. It's not going to change anything in the sort of bounds we'll derive. Okay. So we're going to assume that also the physics is computable at the scale m. EFT is weakly coupled, at least we trust the Lagrangian description at m or slightly below m on this arc that I described above on the contour. I'm going to assume that at that scale we trust we can compute. And if it's weakly coupled, we have a Lagrangian. And let's write down the most general Lagrangian we can have for a real scalar field. And we're going to be assuming Lorentz invariance. So we have something like the usual kinetic term, maybe a mass term, but I told you to neglect it. Could have a cubic coupling. Could be a 5-4 interaction. And then this is the usual relevant interactions in d = 4, for example. And then you have higher derivative terms, like when you start writing them down. Well, the first thing you could write is maybe del square phi square. There'll be some coefficient which should scale like which you expect to scale like some power of 1 over m squared. You're trying to do a derivative expansion in power of the scale. And you can also imagine something like phi, d phi square, maybe over m coefficient. And then you would have other things like d phi 4. A whole bunch of things like this. So here I've done nothing deep. I've just started writing down the most general thing I can write down. And if you start writing this, very quickly you realize something. Or if you try to compute observables from that, the important thing to ask yourself at some point is what are we actually measuring? So in physics and experiments don't measure Lagrangians. And in fact, no. Here you may, when you write down this expansion, you may have some physical picture of what this field is. You know, after the quantum field theory, we start with this bed spring model and so on. Maybe you have some physical picture for what this field means, but in practice, experiments don't measure fields either. They measure some properties of some excitations of the field, which are labeled by the momentum, energy, that we can think of as particles, and we scatter these particles. This doesn't tell us anything about phi. So experiments are defined only modulo field redefinitions. And if you start doing field redefinitions, you realize you can get rid of a lot of these terms. So for example, if you can remove this guy by taking phi to phi plus some coefficient times the Laplacian of phi. This coefficient will go like 1 over m square. And then that will, when you insert this shift into this guy, you would get something like the second guy up to total derivative, and also Lagrangians are invariant up to total derivatives. And you can also get rid of higher derivative term for the kinetic term by adding, you can expand in that, 4, 5, plus dot, dot, dot. So you can do a lot of field redefinition that removes stuff. And that will cancel this. And in general, field redefinition changes the, maybe some reference here that will come in later. Sorry about that. I'll just move it elsewhere. So when you do a field redefinition, you shift the Lagrangian by, so you change the field by adding something small to it. Basically, you shift the Lagrangian by something proportional to the unperturbed equation of motion. Okay, so in general, anything that's proportional to the leading or relevant equation of motion is removable. And in fact, if you take about the cubic coupling, like phi, del mu phi, del mu phi, up to integration by part is the same as phi squared del square phi, which is 0. So you don't even have to bother about corrections to the cubic vertex. The thing that survive are in one-to-one correspondence with on-shell amplitude. So you don't have to write correction to the kinetic term. You don't have to enter in correction to the cubic term, because for scalars, there's only one possible on-shell vertex you can have. It's just some coefficient here. Maybe you can shift the coefficient, but once you measure this on-shell 3-point coupling, there's nothing more. There's no more information. You can always write it in a phi cube form. And then after that, we have that's M3, and then you have M4. So when you look at the 4-particle amplitude, you can calculate the amplitude. So instead of parameterizing things from the Lagrangian, you can also parameterize things in terms of the amplitude. And that's actually much easier. So there's going to be, okay, for example, for the relevant part, well, you could have the phi cube exchange. So if you have a phi cube vertex, you would have a plus g square, and then 1 over s plus 1 over t plus 1 over u. You could have a lambda phi 4 vertex. And then you have other things. And the other things, they will come from these higher derivative terms here. So we can try to list them directly at the level of the amplitude. And up to loop correction, so if you add this thing to it with a small coefficient, if you think of this as a small correction, the higher derivative part just give you polynomial. Okay, and or u if you wish, but u is related to s and t. So instead of listing Lagrangians or derivatives, it's much easier to list polynomials in ST. And actually, you want symmetrical polynomials in STU. So it's easy to list them. So at linear order, well, the only thing that's symmetrical is s plus t plus u, and that's 0. So there's nothing at linear order. You could have deduced that by, you could have entertained things like this. And what I'm telling you is that things like this in your Lagrangian, you can integrate by part and write this in terms of equation of motion and remove by doing field redefinition. There's no content. There's no observable content, no observable effect of this thing. The first thing that actually has an observable effect is quadratic in Mandelstams. And that would be s square plus t square plus u square. That's non-zero, it's a sum of square. And the next order, you only have one invariant, it's STU. And it turns out that it's a nice result. All the symmetrical polynomials that you have are products of these two things. So the ring of symmetrical polynomials in 3 variables that add up to 0 is generated by these two polynomials, the freely generated ring. So our goal is going to be to constrain these coefficient of these things, which map to terms in Lagrangian, like this one. Going to, yeah, maybe I can write it here. Let me rewrite it because it's going to be useful. Okay. So the thing we're going to be constraining, so this, I'm going to talk about this reference in a second, is the thing what we're going to be constraining are low energy amplitude that have this form, plus we call G sub 2 because it has 2 powers of minus 10, S squared plus T squared plus U squared, plus G3, STU, plus G4. So at fourth order, the only thing you can write down is the square of the first one. At 5 order, you can write the cross product. At 6 order, we can write either one of them square or G6 prime, that would be STU square. And you can keep going. It's very straightforward to enumerate higher derivative interactions. And things with more than 4 fields you don't really see at 3 level. This is the amplitude modulo loops. Here I should mention an important comment is that, again, what do we constrain? What we can constrain using self-consistency methods are observables. What we can constrain are observables, in particular, that are going to be linear in the scattering amplitude. Observables are linear in M. In general, we constrain observables that are linear in M. And that means that the things that we actually constrain, they're non-linearly related to Lagrangian parameters. Okay? It's kind of unavoidable, and that boils down to the fact that experiments don't measure Lagrangians. Okay, so that's a bit you might like you might have liked if I could give you constraints directly on parameters in Lagrangian, but I cannot do that unless you tell me what the map is, or meaning you can compute loops. So, well, if you can compute to some accuracy, you can probably work out the relation. But specifically, would be bounding observable linear in M on this arc at S over M square, and momentum transfer T less than M squared. So we're going to be bounding observables that are mostly dominated at the scale M. Okay, and we choose our observables so that they're always bounded, but we'll choose them so that they give in theories that are tree level, in theories where you can neglect loops, they measure individual one of these couplings. We're going to choose our observables so that they're most sensitive to, well, in tree level, they would be sensitive only to one of them. Okay. Let me say a few words about the spinning case here. Okay. So when we have spin, as we saw for the graviton scattering, well, so for example, for d = 4 massless graviton, we cannot always pull out some factor. So for the amplitude of a bunch of gravitons, I'm going to write it again, the same example as we had before. We have something like what's going on? Sorry. Okay. Times F ST, and the amplitude is exactly such that contact interactions are very easy to list. They're simply the things that are polynomial. But the important thing to realize is that you have the spinor factors in front. So that's polynomial. So if you have a constant polynomial here, that's actually this term here. So we could write it as I call it G4 plus dot dot dot. This G4 actually corresponds to a term that's Riemann to the fourth power in your Lagrangian. The constant term is the coefficient of Riemann to the 4. Because you have all these derivatives sitting in front hidden in the spinor product. And you can play the same game for other felicities. So actually different felicities behave very differently. So if you have this plus plus, you have something like this case here, it turns out that the amplitude has some big factor. Then you have some, I actually forgot how it works. It's yeah, you need a lot of fours. You need angle four times. And that I can put here 1, 2, 4 times 1, 3, 4. For this one here, you actually need a lot of derivatives. Yeah, 4, 4. Maybe I will square those, and maybe put a 2 here, and then so I have 1, 4, 2, 1 square, 2 square, and then it's going to work if I put 1, 3 square and 2, 3 square. It has more derivative, and then again you have the constant plus dot dot dot, and this constant here actually is like a Riemann 4 times 4 derivatives. Okay, I will give one last example in D equal 4. If you have a similicity, this one is a bit subtle because now we can write different polynomials. Write 1, 2, 4, 3, 4 square, or 1, 3 square, 2, 4 square. The first one looks like S to the 4. The second one looks like T to the 4 or anything. And they all, it turns out they're all proportional to each other. But you can do a nice ansatz where you can also write them in a crossing symmetric form. Times H of ST. This thing is fully symmetrical, but is has to be proportional to at least 4 powers of Mandelstams for each. So the first contacts give you S4 plus T4 plus U4. Oh, sorry, S squared plus T squared plus U square, etc. That's the Riemann to the 4. So one can work out how this works. A very useful concept of these things that a classification of these things that you can multiply. The general concept that's useful in general dimension is that of a local module. Or for massive amplitude in D equal 4 is a local module. And the idea is that that's a basis of the ring of, well, the module over Mandelstam variables. Take this concept from this very nice paper by these authors, where they classify the module for photons and gravitons in any dimension. The local module is the basis of module over ST for polynomials in polarization and momenta. So a contact term, once you found these generators, it's very easy to enumerate contact terms. You just write all polynomial coefficients. in lucky situations, the module is freely generated, so these polynomials are completely independent. Sometimes it's like this case where you have to impose some, they only start not at the constant term, or the first few orders are not allowed. And that's it. So that's a nice idea. These local modules, they've been there are also some nice construction of them in that's for massive amplitudes in 4 dimension. For D. And yeah, the other paper will come out later. Okay. So what I've described here in the last 15 minutes are a bit the kinematics. And well, how do we enumerate low energy interactions like contact terms Lagrangian? And I think the short answer is don't spend too much time on Lagrangians. If you want to enumerate, the easiest way is to enumerate the observable amplitudes. And these are the things we'll actually bound with these techniques. Other questions?
I have a question, Simon. So in the effective Lagrangian that you wrote down, you had higher derivative terms, but sometimes we really have genuine non-local terms, especially if you work with a gauge theory or with the theory of gravity, in which you have to solve constraints for gauge fixing, which enables you to talk about scattering of spin to objects, for example, with 2 polarizations. Now, so what is the implication of something like that in what you have derived? So that's one question.
Yeah, sorry, can you repeat the first part of your question? So that when there's so you mean situations where you don't just have 2 polarizations?
No, what I meant is that you take a theory of gravity, for example,
yes.
Then depends on your formulation. If you do covariant formulation, you will have to have ghost fields, which are all,
yes.
So the Lagrangian is all local. On the other hand, if you fix a gauge, a physical gauge, which enables you to talk about external particles which have spin 2, so that's already a choice of gauge that you eliminate other polarizations.
Yes.
In such a theory, there are necessarily non-local terms which cannot be just approximated by a derivative expansion. So I was just wondering how what you are saying applies to such theories.
Not sure what you mean. So in Einstein gravity, you can do this derivative expansion. You start with the Einstein Hilbert and you add the things. So there's no, well, it depends whether you write things that are in polynomials in the Riemann tensor or the metric itself. I'm not sure exactly what framework you have. Regarding ghosts never appear on the external leg of a scattering process because they're not BRC closed. Well, they're not part of the Hilbert space of asymptotic states.
That is correct, actually. So you are looking at some covariant formulation of gravity.
Yeah, and we're just putting BRC closed states on the outside.
Yes, that I understand, actually. So which are automatically spin 2. So,
so they only have transverse polarizations. Yeah.
I see. Okay. So you need a locally defined theory basically to do this type of analysis. I mean, if you have a non-local term in the effective Lagrangian, how do you do this?
Well, the way I will approach it is that if you have a non-local term, it probably comes from by a non-local term, you mean perhaps something like 1/p square, or I'm not so sure what you mean. But if you have something like this, I will say that it comes from exchange. I will integrate in the particle, describe it, and say that the effective theory is not just a graviton, but it's a graviton coupled to some scalar or something else that gives these poles. Like usually when you have
so Simon, I think Sventa is referring to something like quantizing, let's say, QED in Coulomb gauge or something, where you solve the Coulomb constraint and you get some.
Yes.
Yeah.
It means some non-covariant propagator.
Yeah. So something. Like
yeah.
that.
Yeah, but these they should cancel out from the S matrix will not have poles at non-Lorentz invariant positions. All the singularities of the S matrix will be in terms of the Mandelstam invariance. We always have an elasticity in the upper half plane, and that's all I'm assuming.
I see.
Yeah.
Okay.
So in some sense, we're trying to be as agnostic as possible about the framework we use. These properties may or may not be manifest in a given framework, but we assume that the amplitude is an invariant thing, and we assume that the amplitude satisfies those properties. You can calculate the amplitude in any framework you want.
Okay.
Yeah, there's also a good question in the chat that rightfully points out that amplitudes are correct. Physical observables are quadratic. An example? Can we give an example that's linear? And well, the point is that if you think of these as small corrections, then the interference term between the interference term is something that is linear in G2 but quadratic in the amplitude. So in that sense, we're going to treat the amplitude itself as observable, because in principle, if we assume we know this low energy part, we can measure the interference. So yeah, we can imagine observables that are linear on these corrections. That's how we're thinking about it. Okay. So I'm going to say a few things about the high energy part of the sum rules and then how we actually use them. So like the goal is we have some rules that relate low and high energy parts. And maybe I should, before we move to high energies, I should say, I should record what we get. So if we put this scattering amplitude that was here, and if we plug into these sum rules, we go back to the left, we just have this contour integral. And well, at 3 level, this is just like a contour integral. It's really just going to pick residues of here instead of having a cut, we just have poles, which is going to pick residues. So it's very easy to calculate and just get some residues, and you just pick out these coefficients. So you get things that looks like this. So when you compute B2 of minus B square as a function of the low energy contribution, well, minus the low energy contribution would give something like G2 plus P squared G3 plus P4 G4 plus dot dot dot. So you get some infinite series of terms in terms of these higher and higher derivative terms. Okay? And this thing here, the spin 0 exchange don't contribute because B2 has spin 2. It converge, it kills all exchange of spin less than 2. So we just the exchange diagram is just killed by all these sum rules, and similarly the minus lambda term is just killed. How do you see how the things would grow like S square or faster? So effectively, this extracts the quotient of S square. Then you can write other sum rule which are more subtracted. Here I have an amplitude that is crossing symmetric, so I don't have odd spin sum rule. And the next one here will be G4 plus P squared G5. So you can make these sum rules like this. So now we're going to compute what these things are at high energies, and we're going to equate the low energy and high energies. So at high energies, what do we know? Well, the idea in effective field theories is, well, sometimes we know you integrate out something, but here we oftentimes you also oftentimes in effective theory you have no idea what happens at high energies. Like when you try to model, when you try to look for corrections to the standard model at colliders, we have no idea what's coming next. We have no idea what the energy theory is. So we just so we're gonna take this attitude there that we're agnostic about high energies. So at high energies, the only thing we have are symmetries and partial waves. So we use symmetries to express things in terms to do partial wave analysis. So we can write the scattering amplitude at any energies, but at high energies as a sum over all spins times some coefficient times some normalization, depends on J, times some spherical harmonic or scalar, for example, it's cos theta. And the cosine, this coefficient in general will depend on the energy. And this Legendre polynomial, or this narrow dimension Gegenbar polynomial, just like a spherical harmonics. And cosine of theta here would be 1 plus 2t over s. And just like this. And this normalization I will not write down explicitly here. You can look it up. The reference I gave, analytic toolkit for this matrix, nicely gives some consistent conventions. And idea is that all the dynamics sits in this thing. So the question is, what do we know about this these coefficients? And well, when we normalize them properly, we can take remember that the S matrix is 1 plus IM. We can take the S matrix that when acting on the in state that is that has angular momentum J, that has energy S and spin J, you get 1 plus I AJ of S times spin state. Okay. So we can normalize this normalization factor. Basically, there's a natural convention choice for it, such that S matrix on partial wave J is just 1 plus IJ. And then the fact that this is less than 1, because S is unitary matrix, and this is like a one matrix element of it, one diagonal matrix element of it, implies that the imaginary part of HA is positive and also bounded above. So this is all we know about the UV. So if we take the imaginary part of M in the UV, we can write it as a sum of imaginary terms. And all we know is that these unknowns are positive and bounded. So this is all we know about high energies. And we're going to find ways to use that. I'll come to that in a second. Before I do that, maybe let me mention what changes in spinning case. So the general way to think about partial waves in our dimension is that it's about, so we're doing a scattering process, time goes up, something happens, something comes out. The idea is that we're inserting a complete basis of state in the middle. And these states here are labeled by their mass or square root of S, the energy, and the spin. So the kinematics of how, so the important thing to understand when we sum over this basis of states is how this intermediate state of mass M and spin J couples the things on the outside. And that is exactly the, kinematically, it's exactly the same problem as looking for 3-point couplings between massive particle and the external ones. Okay, so the partial waves are in one-to-one correspondence with couplings between one massive particle and the external one. Between a massive particle and 2 external ones. And this can be enumerated using Lorentz symmetry and group theory. In 4 dimensions, these couplings are very restricted, especially when you have massless external. There's a nice classification by yeah, so I say a few things about this in 4D. There is a natural classification in terms of helicity. So if you go to the rest frame of 2 particles, even if your incoming particles are massive, if you terms of helicity, even if they are massive, and what you get here, so the helicity is the spin of the particle relative to the axis. And if you're in the rest frame, they're back to back, so there's only one axis. And the spin in that axis is like a SO2 symmetry that you can diagonalize. In terms of this helicity, you just get so-called Wigner D functions. And they arise nicely in terms of spinor helicity variable. This is explained in detail in the paper by Kanyamed, Huang, and Huang from that I cited in introduction. And in higher dimensions, these couplings are best thought of in terms of Young tableaus, because the intermediate particles are Young tableaus. Okay. And you can roughly understand the coupling between the Young tableau in the middle. So in that particle here, you have a SO D-1 Young tableau. And here you have to work out couplings. And well, depending on whether they're massless or massive, it gets more complicated. But mostly, well, the case needed for photons and gravitons have been analyzed in the nice paper by this paper here. Okay. So yeah, so there's put it at a more relevant location. Okay. So this thing can be classified as some group theory problem. And once you have the 3-point coupling, you sum over intermediate state and you get some special function, which you can write as like derivative of Gegenbaur polynomials. It tends to get complex, but still it's still almost infinitely easier than what you get in the conformal bootstrap problem, where people have solved analogous problems. So it's something that can be dealt with. So the kinematic aspects of the S-matrix bootstrap is a nice, it's non-trivial, but it's something that can be done. So that's a great news if you want to do that. So to illustrate the next idea of what you do with this, I would focus on the scalar case, where this is very concrete and explicit. The spherical harmonics are just some 2F1 thing. Okay, and so the idea is that we write a and some power of d. The idea is we can write. Let me see. We equate this to the sum rule to the integral over the imaginary part of the amplitude at high energy that represent the sum rule at high energies. We end up with like us main things that b too low is equal to I, and that gives some relation along the line of G2 plus G3P square plus G4. G4 plus dot dot is equal to an integral over all every states and the mass of the every states. Then you have some imaginary part of AJ, it's coupling, sum over spin. It's going to be a lot of factors. Times basically a Legendre polynomial of, and here going to write downstairs, going to be some Legendre polynomial 1 minus 2p square divided by some power of m square, and yeah, like I like to put m square. Power of k. 2. And I'm probably missing some factor, but that's roughly the integrand. Actually, you get the average of those two things. It's 2m square minus p square. So that's the u minus s factor, s minus u factor. So you get something like this. In order to not get too bothered by notation, the only thing that's going to be important for the discussion to come is that this thing is like a positive measure. So I'm just going to abbreviate this thing as okay. Maybe I should put some power. Yeah, I'm just going to put some power. Okay, and this average just means that it's some sum over. It's not really an average because there's no natural normalization, but it's a sum of positive J and M. Okay? It's average over all heavy states. So they have mass above this delimitation. And we have and here all the spins are even.
So there's a question in the chat.
Yes. Are the higher dimensional analogs of finger D functions known? I don't know. I try. All I know is that you can write all these partial waves in terms of the Wigner functions. You can actually write in terms of derivative of Legenders. It's not a very useful way to write them, but you can. In higher dimensions, you can always write the answer in terms of derivatives also. There must be a more clever way, but that's all I know. If someone knows a real good analog, that would be great. But it's got to be a bit more complicated because in higher dimensions we have Young tableaus that I get paired, not just it's not so clear how to put the information of a Young tableau into a function that's as simple as a 2f1.
So Simon, can I ask you a question as well? So this sum over spin that you have here, that is sum over all spins, or is there a truncation in spin?
It's over all spin.
And here, are you assuming that the sum over spin converges? Or what is the logic?
That's a good point. Yeah. Okay. The logic is the following. Okay. Yeah. So the logic, well, the correct logic is that, remember that we're supposed to smear the sum rules, they're not valid yet. And the smearing against a wave packet that is normalizable is going to suppress the large spin contribution. Smear against normalizable wave functions. And that's going to be that's going to make things convergent at large spin. Because these Lejeune polynomial at large spin, they oscillate very violently.
I see.
So anything that is smooth and anything that is normalizable in impact parameter space means that it's smooth in P, so it's going to cancel out.
Okay, and the argument just uses the fact that AJ is bounded. AJ is less than 2. Yeah, okay.
Exactly.
Thanks.
So AJ is bounded, and then the PJ themselves are
okay, thank you.
average out something small. Yeah. So that's the correct logic. That's what we imagine doing, and that's what we actually do when we try to bound gravity. There's a cheap logic, which is to just do Taylor expansion around the forward limit. It's widely believed that this is correct when you neglect loops in the EFT. It's something that should be clarified. But the basic idea is that as long as you neglect loops, there's no reason for things to blow up in your face. So you can, if things don't blow up at low energies, then okay, you can assume that they're fine at high energies. But I think this is, I think things you can debate. So for example, well, you could also maybe I can also let me explain a few things here. So even if you have a mass gap, if you exchange like particles, so at one loop, for example, if you can exchange a light particle of mass, let me call the mass not small m because I already use small m. Let me use a mass mu here. If you exchange a particle of mass mu, you get an amplitude that decays like x of minus 2 mu b at large b. Or currently there's a pole 1 over p square plus mu square at small, but it has some singularity. It's not quite a pole, but it has quadratic singularity. And at small p, or it goes like 1 over mu square at p equals 0. So when you exchange a particle of mass mu, if this particle is much lighter than your cutoff, you get something that's quadratically divergent in the forward limit. And that happens at all energies, whether you're above or below the cutoff. It's kind of unavoidable. And the square here in general is d minus 2. Maybe I should put this number of perpendicular dimensions. So if you exchange a particle of mass mu, you get a total cross section of that goes like 1 over this mass to the corresponding area. Okay. So we get, it's very natural to get at loop level. I mean, whether you have a mass gap or not is kind of irrelevant because the light loops, whether they're massless or not, they give you things which don't satisfy the EFT power counting. We're trying to bound things that involve powers of the EFT cutoff. So like we're trying to control this coefficient G2, G3, and we expect each of them to be expressed by powers of this, there's some power of the mass, of the large mass that we expect in these expansions. So if we start to have contributions that are enhanced by 1 over some light mass, like the neutrino mass or the electron mass in standard model, this approach is really not good. But so there's a limitation. So this cheap logic does not work at loop level. Okay, so it works if you neglect loops. It really does not work if you include loops. But we're going to assume that it's still close enough to correct logic that the conclusions are correct. And this is to be justified by studying things using these smeared wave functions. And maybe if I can give the punchline already, what we get are basically the same bounds. So I think the cheap logic is correct. But it would be nice to analyze loops further to really be sure. But in the end, we always find the same bounds whichever approach we take. So we're going to describe the easier bounds, well, at least the easier ones to justify. So if we Taylor expand this thing around the forward limit, when you expand both sides in P, you just get some polynomials. And the nice thing is that the legend polynomials at 1 so are just 1. It's positive, and the derivative have nice sign properties. I emphasize that this is not true in general. Like, we're not saying that the imaginary part of the amplitude is positive here. It's a sum of positive unknowns times oscillatory functions. In general, when you use these smear wave packets, we have to work to make positive combinations of the unknowns. But when you expand around the forward limit, if you just take if you just take P equals 0, you get that G2 is the average of 1 over M4. So sort of some rules you get looks like this. You get something like G2 is equal 1 over M4. Then you get G3, maybe something like some normalization. I forgot the number here. 3 minus J plus 1 over M6. It depends on the space-time dimension. Maybe I should write D minus 3. This is a Casimir. Then you can write G4. Maybe in the way defined as a factor half. And actually, there's something interesting that happens. When you start listing these sum rules, what you discover is, so here, let me scroll back here. I have the expansion of the amplitude. You can write different sum rules for G4. So you can write this sum rule here roughly, which extract, or this sum rule on the left here. This sum rule extract the quotient of S, the 4. In the amplitude, in some fixed T dispersion relation, whereas this thing here extract the quotient of S squared T squared. And a priori, these would be independent coefficients, but they are related because the amplitude is crossing symmetric, and there's only one symmetrical polynomial at order 4, at degree 4 and minus times. So these coefficients are the same. But that means that there are two different ways you can measure G4 that are related to each other by crossing symmetry in the infrared. When you combine these two ways of computing G4, well, the difference between them is something that has to average to 0 in the UV, and that goes like, let me call this thing J square. It goes like J square times some J square minus some number over M8 is equal to 0. And then you can list infinitely many other constraints from crossing symmetry. So they encode crossing symmetry in the infrared. This looks a bit weird because this is a constraint on the UV that comes from the requirement that the infrared is crossing symmetric. It feels a bit like a UV IR mixing, but I don't like to think about it like this. It's really because we're scattering IR particles, and the thing that what we're learning from this is that the coupling between light particles and AV particles knows about crossing symmetry in the infrared. So I don't think it's a particularly deep statement about mixing between scales, but this average is not arbitrary. So this is something else we know about the UV average. It has to be consistent with crossing symmetry in the IR. Not just positive, but consistent with that. So I'm going to finish soon. So what do we do with this? So dealing with this sort of equations where we have positive unknowns and a bunch of constraints and some things you care about, that's a general template of a bootstrap problem. So there's a bunch of ways we can use this. The first is to find the clever positive combinations, find clever inequalities, clever ad hoc inequalities. For example, I'm going to just exemplify this a little bit. So for example, since the average is over states that are heavy, the things that we don't know are the things that are above the cutoff. It's kind of obvious that 1 over M8 is less than 1 over M4, capital M4, for M greater than capital M. And that implies that G4 can't exceed G2 over 2M4. So the coefficient of more derivative has to be suppressed by more. So you can find a bunch of ad hoc inequalities like this. You look at the one for G3, it's also obvious that G3 is less than 3G2 over M squared. But then it's less obvious what's the lower bound on G3. And if there's a lower bound at all. And according to dimension analysis, you would expect this higher derivative correction. So G3 is a quotient of like 6 derivative of phi 4. Remember that Lagrangian as G4 times d phi 4 plus G6. This quotient is, sorry, G3 is a 6 derivative term. You'd expect this term to be like suppressed by, more powers of the then you'd expect this G3 to be bounded both ways by some order 1 multiple of G2 over M squared, but this does not follow easily from these bounds here. It turns out that using Cauchy-Schwarz, that we described this in our paper with Vincent, and also in the there was another group by Shuyang Zhu and Andrew Tolley and others that from Imperial to derive at the same time. Using Cauchy-Schwarz and things like this, you can do a bunch of you can prove things. But it's not very systematic, and you never really convince whether you explore the full options. So next thing you can do is numerics. Some systematical numerical exploration using some tool called linear programming. There are other things you can do. You can do some, you can analytically find boundaries. So notice that all of these average that we have here, they are like polynomials in J times polynomials in 1 over M. So the average of polynomials is a whole mathematical theory of that. So this is called a moment problem. Here it's a double moment problem. So there's a paper by Yutin Wang and collaborators that I think cited before that discussed this a lot. And what you can find here is you can analytically find some boundaries. You can list boundaries. However, even after you listed the boundaries, like it's an infinite list of boundaries, and until you've been through all of them, you don't know whether you have the optimal bounds or not. So in practice, you still want to combine this with a numerical exploration just to see that you actually have the optimal boundaries. And then there are other approaches, for example, by Aninda and friends about geometric, were proposed to use crossing symmetric dispersion relation and geometric function theory, things that I will not explain. But even then you get some results, but you still want to compare these results against. It's still good to have some systematic numerical exploration of constraints. So that's what we'll discuss tomorrow. Before I leave, maybe I want to describe a simple thing that can be proven by Cauchy-Schwarz. That's actually very nice. Okay. So I'm just going to use that null constraint, which remember encodes crossing symmetry. We'll be finishing in 2-3 minutes, if that's okay. If you take this and you combine with Cauchy-Schwarz, so roughly speaking, you can see that this some rule prevents the spin. It balances low spins against high spins. So it prevents the average of spin 4 from being too big. But we also have Cauchy-Schwarz tells us that the average of J square over M6 square is less than average of 1 over M4 times the average of J4 over M8. So basically there's 1 over M4 that's passive here. So maybe I could write it differently. So if we let, it's useful to define a quantity that's impact parameter, that's 2J over M. If you define an impact parameter that way, it's basically telling us that B square over M4 is less square is less than 1 over M4 times B4. That's kind of intuitive. You see that 1 over M4 is positive. And so you can do things like this. And let me get it correctly. Exactly, yeah. And this null constraint here tells us that the right-hand side is less than average of 1 over M4 times a multiple of B square over M4. So we can cancel 1 power on each side, and you end up with the following very nice inequality that the typical impact parameters of the thing you can produce is less than a constant times the average probability that you produce something. That's going to be a very powerful relation. It means that as far as EFT coefficients go, or as far as they care, as far as EFT coefficients go, heavy states have size less than the cutoff. States with S greater than M square have size B less than 1 over M. This should shock you, because we know many examples where we have extended states. For example, extended states. For example, in string theory, we have states with size grow logarithmically with energy. Eventually, at higher energies, we have black holes whose size grow like a power of energy. And what these things tell you is that all of these sum rules have sufficient power of 1 over M4 that they basically don't care. So all of these extended states that you worry about are lying there. They exist in the high energy regime of these theories. They never dominate dispersive sum rules. And that's a consequence of crossing symmetry in the infrared. That's the first lesson we obtain here. This lesson will be very interesting next time, because, well, it allows us to bound effectively the spin in this. So this null constraint here allows us to bound the spin in these sum rules. And once you bound the spin effectively, or then more precisely the ratio J over M, the impact parameter, once you bound that, you get two-sided bounds on everything. So, and these two-sided bounds, well, they justify the EFT power counting. So, but yeah, I think it's a striking message. You could have worried that crazy things do happen in the UV, but they can never matter for these sum rules. So thank you and see you tomorrow. Never look at the exercise.
Sorry, Simon, can I ask you a question?
Yes.
So you made a statement that you get two-sided bounds on everything. Where I mean, I can see that you can check case by case that these Cauchy-Schwarz inequalities will give two-sided bounds.
Yes.
But where is this everything coming from?
Oh, it's just yeah, induction. I stop at order 10.
I see. Okay. So, but yeah. So you're saying that since you check from order 10, you expect that everything will be also bounded. Yeah.
Yeah.
Okay.
That's it. Yeah. Sorry, don't have a better answer. It'd be nice to have an actual proof and so on.
No,
think
I just
Eugene
wanted
and
to
Friends-
clarify that. Yeah. Okay.
Yeah,
Fine.
yeah,
Sure.
yeah.
Thanks.
Yeah,
Thanks.
I think Eugene and friends actually prove more statements about the large order, but we just yeah. We went
Yeah,
up to
we have a
10
general
elsewhere.
argument why all
Yeah,
coefficients
also,
should be
yeah.
two-sided bounded. Yeah, from GFT
Oh,
arguments.
okay. Okay,
Yeah.
that's good. Yeah. Okay. Yeah, the thing that we found nice with these bounds is that they don't grow with the size with the coefficient. So if they like, I mean, there's a geometric growth with the power of 1/m that you expect, and that's it. So because of that, we didn't really expect surprises.
Right. And also, I wanted to clarify your comment. So this should shock you. I mean, you said that we have extended states like strings and black holes that we generally expect, but these are not going to dominate these dispersive sum rules for these low energy, the first few coefficients. But that is expected, right? I mean, I don't see the signature of strings in low energy scattering experiments. So why did you say that it should shock you?
Well, maybe, I think it probably would have shocked maybe some people because yeah, if it doesn't shock you, then that's good. You have the correct intuition. I was
No, I mean, I
shocked
just wanted to
this.
verify that too. Why? I mean, why is it shocking that low energy, you don't see the sign of extended states in low energy experiments? I just wanted to clarify. Okay, thanks.
Yeah, but yeah, a lot of this is that like you're doing an EFT with some cutoff capital M, and basically you are you take, physics is largely local in scales. So what this is telling us is that indeed it is pretty local in scale, and the scales that dominate, it's largely because of this 1/m4. The states would dominate the sum rules are the states that are very close to the cutoff.
Mm-hmm.
And we're thinking about the cutoff that's less than the Planck scale. So there's just no black hole close to the cutoff.
Okay.
So that's intuition. The things that dominate are the states that are closer to the cutoff.
Okay. Okay. Thank you.
So I had a question. Like, so this kind of a conclusion, does it change if I allow extended objects as external particles? Let's say I scatter a particle against the plane or something, some membrane or something like that.
Oh, okay, yeah.
So like we scatter strings against D planes, right? Something like that.
Yeah, it's a good question.
So,
I don't even know a framework we can do this scattering experiment. The closest I can imagine doing is you can scatter, for example, excited string scales that are like strings of finite length, but they're still like particles with finite energy. I would not know how to scatter a brain of infinite extent.
but this analysis, this EFT analysis, could probably be, adapted to that kind of a question, right? S matrices with just planes and boundaries and.
Oh yes. Okay, I see what you mean. Like a presence of a defect. Like so yeah, you will you scatter a graviton and let it bounce off a brain.
Yeah, say.
I think so. One would have to figure out exactly what the causality criterion is. I think the only thing that we really constrain is the amplitude where the where it doesn't bounce, because like if you have something that bounces off something else, it's not true that the commutator of these measurements vanish, because after it's bounced, it's become time-like from where it started. You have to draw, I'm drawing with my end, sorry, that's probably not very clear. But if you have a brain and you scatter a graviton of it, you cannot take a commutator of, it's not true that phi1 and phi3 commute. but the things that you can probably constrain are things that look like this, where you have you can ask that there's no time advance as you, or the wave does not advance as you cross a brane.
Mhm.
Yeah, when you have reflection, I'm not sure what the actions are. Maybe they are nice actions, but I don't know them.
But even in the first case, one can say that you can't scatter off a brane and kind of go faster than the universal speed or something like. I mean, can't like you should at least take as much time as light goes from these two axes in the first picture. Something like that. Can't
Yeah,
you
but
say?
this seems confusing to me, because how do you know where the brain is? The brain is fluctuating, so maybe you hit a quantum fluctuation where the brain is here, and then you bounce here.
Yeah, but I'm just saying between x1 and x3, let's say I
Yeah.
calculate the light crossing time, direct light crossing time.
Yes.
Wherever the brain is, I should not be able to scatter and kind of, you know, like
Yeah.
come to x3 before light does. Like something can't
The
we
light
say?
crossing, yeah, but that's you're referring to the time, the light crossing time between the input state and the brain, right? And then you double it.
No. I'm talking about x1 and x3.
No.
The
Yes. Yeah. Oh no, but if there's reflection, there's effectively no light crossing time between them. You could imagine they're measuring at the same point. I mean, you could put x3 closer to the brain, but then it's not a symptotic state.
okay. Mhm.
No, the only constraint is the only causality constraints I know are from near forward scattering,
Mhm.
because then there's a real chance that you exit the light cone.
Mm.
Here, the future light cone of x1 is just too fat. There's no chance that you exit it. There may be some extra constraint. This come back to the discussion that came up the other day about locality. Here, I'm just trying to put the minimum, which is causality near the light cone. Maybe there's some notion of locality that tells you cannot reflect before you hit the brain, but I don't know how to formulate this mathematically.
Mhm. But if you have a transfer separation, you can still do it. Like maybe, you know. I mean, I'm imagining x1 and x3 as separated transversely or something. But anyway.
Yeah. It seems hard as long as x3 is the future light cone of x1. I don't. It seems hard.
Okay.
With causality alone. Yeah.
Okay, good.
Yeah, thanks for the question.
Are there any other questions? Okay, I don't see any other questions in the chat or this thing. Okay, so then let us thank Caron-huot for his lectures, and we meet next at 3 o'clock Indian time for the lecture by Masahito. Thanks everybody.
Thank you. Bye-bye.
Bye.